So it's due on Tuesday next week. Okay, so if you have any questions over the weekend, just email me. Okay, so we are almost done with this part of my part of the lecture. So I think we can go to the next module, the module 4 that I'll call today. So we are about, yes, scintillators. So let's actually start from here. So scintillators are basically, crystal that converts high energy photons to, lower energy photon, typically in the range of visible light, and like some of scintillators making scintillation light in the UV range of a light. So there are a lot of different scintillators that are actually really being very actively used. Actually, SPECT imaging, PET imaging, and also CT and X-ray imaging, they all use a scintillator as a kind of stopping material, this converting material from high energy X-ray, high energy gamma ray to something we can detect with conventional photodetectors. Some common the scintillators we talked about, first thing was sodium iodide. I talked about is cesium iodide. And then BGO was the first crystal used for the first commercial PET scanner. It's very good material. It's very high stopping power. But the problem with BGO was it's a slow time, the scintillation, like decay time, rise time. And also it's a poor light output. This is actually the reasons that these days BGO is a lot less preferred as a scintillator of choice for PET imaging. Zinc sulfide was the first scintillator used to produce images from scintillation kind of phenomenon. It's like not like medical imaging, but that's why I have actually zinc sulfide here. So this is what I was trying to say, like in overall, like a scheme, the picture here. So scintillation photons. So now we understand that there is some high energy photons, X-ray or gamma ray. Let's say gamma ray, high energy photon from radioactive material. So now that interacted with the scintillator somewhere, and then the scintillator now has a scintillation photons, right? Now, let's see how those scintillation photons are detected and to make signals all the way to the voltage signal that we can just read it. So for that, we use conventional photodetector. One of them is a photomultiplier tube. PMT is acronym for the photomultiplier tube. It's a tube, as you can. This is a glass tube, meaning that this is made in really facility that they can handle like blowing the glass. A lot of this process is not about the electronics, like electrodes inside of it, but the glass part is a very manual process, as far as I know. So it's glass material, and within this glass material, this is the photo detection mechanism. So scintillation photons, like light, visible light, is hitting the photocathode. This is a photocathode material, like a cesium iodide or some of the material known to be converting, again, with the high energy, like a high voltage applied. What the photocathode does is that it converts scintillation photons to photoelectron. Okay. The same concept is being used, but we are talking about some different energies for the photons. So this a lot lower energy photons still can be converted to the photoelectron by photocathode. Whenever you see the name cathode, it's related to negative charge. So negative charge being electron here. So electron is coming out from photocathode after interaction of scintillation photons. So now there's electron. You have to drift this electron but drift all the way to connect to read out the electronics. But a lot of detection mechanism, we can also amplify the signal. I mean, there even the conventional like data collection like electronics. If you have a weak signal, you want to amplify the signal before you actually read and record. So the PMT does actually that job as well. So electrons are coming out of a photocathode, and those are amplified through the steps of a dynode. This is called dynode. So electric field is applied from this first photocathode to dynode, and the first one to the second dynode. There's also electric field because the voltage is applied all the way across, from photocathode all the way to anode there. So there's cathode, anode, those two main electrodes, but inside there are this smaller electrode called the dynode. So between the dynodes, with very high voltage applied, so electric field, remember that proportional like region of it's basically gaining energy when electron is flowing through electric field. So its energy is high enough, and there's some charge amplification there. So you can amplify the charges over and over, by having multiple dynodes in between cathode and anode. Okay, this is the operational principle of a photomultiplier tube. So at the end, there's anode which is collecting all the charges and then flowing this to the readouts, the electronics. Right. So let's look at the some of calculation like methods about actually try in order to understand the what kind of amplification we are talking about. So what we know, what we have to know about the PMT is that we actually want to know about from the scintillator, first of all. So what's like a light yield? How many scintillation lights are produced per given energy of incident high energy photon? When we talked about something is brighter, some scintilla is brighter, some scintilla is not brighter, or the brightness is a light yield. So two most common examples to compare about the light yield again are sodium iodide, which produces about 38,000 photons per 1 mega electron volt of energy. And then actually less bright material like a scintillator is BGO. BGO is a lot less bright. So if you go back to the BGO property, I can show you this chart again. Between sodium iodide versus the BGO, this is light yield. How many photons are generated per given energy? The BGO is not that bright, right? It's a lot less bright compared to the sodium iodide. This is what we are talking about. So this is number, like conversion factor we can use per given energy. This is just per given, for MeV, this number. So if you know the keV value for the gamma ray from the certain radionuclide, you can tell how many photons we are talking about per that one single gamma hitting the scintillator. Okay, that's what I talked about, the light yield of a scintillator. Now, the next thing you want to know is the quantum efficiency of the photocathode. So let's look at this diagram one more time. So we want to know how many scintillation photons are generated per given interaction, assuming we know that the energy of the incident high energy photon, right? Now, these scintillation photons are hitting the photocathode. Of course, there's some loss because these scintillation photons are not entirely directed to the photocathode. That's another factor. But once it's hitting the photocathode, there's conversion happening from photon to the electron, from scintillation photon to photoelectron, right? That conversion factor is usually known as a quantum efficiency. So if you know the quantum efficiency of a photocathode, usually quantum efficiency of photocathode of used in the PMT is about 10 to 30%, roughly 20% for the ones we are actually dealing with. So the quantum efficiency in here of the photocathode is defined as a number of photoelectrons emitted from the photocathode over the number of incident photons. So multiplication of a single dynode is actually what is the factor? Each time the electrons are amplified by this dynode step, right, stage, then we want to define how many electrons, like a multiplication factor. Is it amplified like 10 times, 100 times, 1,000 times? That's the factor we are talking about. This multiplication factor delta is what we defined here. So, and then how many dynos stages we have in the PMT? It's also typically between 10 to 12 dynos we have in the typical PMT. So we now know everything about how to really calculate the signal generation, like amplification factor, by the photomultiplier tube. So over gain of the PMT is defined as a fraction of photoelectrons collected by the dynode structure. That alpha there. What does that mean is that if you look at this diagram again, we can assume that if we design the PMT very carefully, all the photoelectrons generated from here could be directed almost 100% to dynode, but there could be some loss. That's why we want to put some alpha there. And then we want to also have this number of dynodes there to know that the more dynodes, the more you can have more amplification, right? That's that n factor. And each time it has a delta amount of multiplication. So let's look at the some example. So let's say alpha to be close to 1. As I said, that if it's a well-designed PMT, that alpha in this equation should be close to 100%. Delta is like a multiplication factor of each time when dynode amplification happens. So let's say that it's about 5 times of amplification for one dynode stage. And then if we have 10 dynodes, like number of stages, this amplification stages in the PMT is to be 10. Then over gain for that PMT is about 5 times to 10, the order. So it's about 10 million amplification. Why, again, the reason we want to amplify the signal is that we are really talking about very weak signal. If you, we calculated like a Coulomb, the charge from one one single quantum of interaction before. It's pretty low value. So without the amplifying, like electrons, basically making more charges, making basically bigger current, that way you can measure some measurable voltage out of any electronics. So this calculation is pretty much corresponding to the measured typical photomultiplier tube's gain, which is roughly about 10 to the 5th to 10 to the 8th, really depending on how many stages of dynodes there, and then how well we design these multiplication steps, and then like a voltage apply, across the photocathode and then anode of the PMT. So this is another more practical example. So let's say that this is all the way coming from the high energy photon from a radionuclide. Now we have one gamma ray, the photon, from technetium-99m. So let's say there's 140 keV photon hitting the scintillator, sodium iodide. Okay, what kind of signal we are seeing at the end of the anode of a PMT is what we want to calculate. So current is what we are interested in. The current is coming, basically flow of the charges at the anode is feeding, is being fed to the electrical circuit. That's the current. That's what we want to know. So let's do some calculation based on, this very simple theory we developed. How many scintillation photons are coming out of the sodium iodide? This is 140 keV. So we know that the sodium iodide produces about 38,000 photons per MeV. So that's that calculation. So 140 keV photon will generate 5,320 scintillation photons. Let's say that in all of these photons, this is a not really great assumption, but all these photons are going to the photocathode. This is not really true. As I said, that scintillation photons are more like an isotropic distribution. There's only PMT at one side. It's not actually ideal. But let's assume that all of these photons are going to the photocathode. Now what we want to know is that how many photoelectrons are generated from photocathode. For that one, what we have to know is that the fraction, we assume almost 1, but the quantum efficiency of the photocathode is the most important factor there. So let's say that that's about 20%. Okay, quantum efficiency is about 20%, and alpha to be just assumed to be just 1 here. So photoelectrons after the photocathode now in this calculation is about 1,000. The number you are seeing, like 1,064, is just 0.2 times 5,320. Right? This is photoelectrons from the photocathode. Now we do multiplication steps in the dynode stages. So let's say that our PMT has a gain of 10 to the 7th. That's another like a value I added there from our previous approximate calculation. So let's say that at the end of the PMT, the anode side, we have almost 10. Now it was 10 to the 10th. The amount of really number of electrons there. Now we want to know the current. How can you actually calculate current? We have to know the rate. So let's say that the rate of the signal collection is that, let's say that the signal from the sodium iodide is collected over 1 microsecond. Then we can really calculate the current, really being fed to the electrical circuit. So when we have rate information like that, then we can apply the rate information to get the current information. So we know the charge from one single 140 kV photon, but if we really measure this one at the rate of 1 microsecond, so we know each electron carries about 1.6 times 10 to the minus 19 Coulomb charge. This is rate, right? This is the current we are talking about, 1.7 milliampere. This is not too bad, but without actually amplification, think about that. Amplification is 10 to the 7 by the PMT, right? Without that, this number is not even milliampere. It's not even like a microampere. It's like a picoampere. It's a lot, the nano pico level that we are talking about. It's really hard to detect because all the electronics have basically some baseline noise there. You have to make sure that your signal should be at least over the floor of the noise level. It's a simple calculation, but this is pretty close to realistic number. This is also the part that I'm not going to emphasize a lot, for the class here. But there is always a way to. So again, the emphasis is that the current is what we can get from the detector, but this current should be read by the readout electronics. And then readout electronics, the actual signal at the end of electronics is the voltage measurement. So you have to know how to actually calculate the voltage out of it. This is kind of pulse shape. This is all, just kind of a signal like pulse we can expect from our readout circuit. Okay, let's skip that. Let's go into, more about describing these multiple, different actually types of photodetectors. We just talked about photomultiply tube as one good example for radiation detector, coupled with the scintillation crystal. PMT is one. But we can have some other types of photodetectors for the same purpose. First example I showed listed here, not showed listed here, is a little more sophisticated PMT. You can actually make a compact PMTs, but combine, like tile these PMTs like individually together to make a, not like a whole thing, but you can make a multi-anode PMT. I can show you some structure there. But this is basically, tied up of internal structure PMT to make one big device, not really big, but one device that has a lot of diodes, but a lot of anodes. So you can actually make a so-called position-sensitive photomultiplier tubes. That's one. as a replacement of PMT as a photodetector for this radiation detector, people have used silicon photodiode or avalanche photodiode, PD or APD, or solid state photomultiplier. This is not tube. This is a solid state photomultiplier. So the name usually for this solid state photomultiplier is like a silicon photomultiplier is another name. There's a reason that because silicon is used for photodetector mechanism there. Or Geiger mode APD is another name. Multi-pixel photon counter is another name. There are a lot of names for this one because when people wanted to use this solid state type of a photomultiplier as a photodetector to replace PMT, what happened was that there are, of course, multiple commercial companies trying to make their own version of this technology. So whenever you have something made commercially, then you want to name uniquely for your product. So that's why people use the different names. Some people say this is a silicon photomultiplier. Some people say our product is Geiger mode APD. These are all the same thing in terms of technology. Or some say that our device is called multi-pixel photon counter, MMPC, whatever, MPPC, not MPPC. Anyhow, but in the scientific community, we typically say this as a SSPM or SIPM, silicon photomultiplier or solid state photomultiplier are much more common names that we prefer to call for this technology. Let's review about this position sensitive PMT or multi-anode photomultiplier tube. So as I was trying to explain briefly about this technology, as you can see, there are many also pixels in this device. This is PMT. This looks a little different from the PMT picture I showed you before. These are real picture of the PMT right there. That's the different types of PMT. Usually PMT is like this shape. But if you make this internal structure and multiply by like a tiled up fashion, what you can make is this multi-anode or position sensitive PMT. And that could just look like this is one example, like this. So each individual rectangle there is the one internal structure of those dynode chain of PMT, single PMT. And then it has the multiple anodes corresponding to each rectangle. So each rectangle could be just read as one pixel. That's why you can have a position sensitivity of the signal because you can read each anode separately. That's how you read the signal. So that's the reason that the position sensitivity is preserved in here. Another example of a photodetector is a silicon photodiode. Silicon photodiode is a very simple form of the photodetector. You just use silicon material. So this photodiode is silicon. So you have a scintillator and silicon combination. And then this photodiode, the silicon material, is also has a high voltage applied across it. So silicon is semiconductor. So if you have a very high voltage applied there, you can actually make the charge going through there because it can function as a conductor, right? So you can really imagine this as a very simple principle of doing photo detection. So you have a scintillation light coming in, and silicon also acts like kind of the photon absorber, and then there could be some charge generated by the voltage applied. You can actually create those the electron hole pair. They can be drifted to be collected to read our signal. This is simple, the way of operation. But usual silicon photodiode operation is that we apply the voltage not that high enough, so we are not amplifying any signal within the photodiode. This is actual conventional operation of a silicon-based photodiode. This is what I explained about semiconductor properties. When you have a semiconductor, the gap between conduction band and valence band is small enough. So when you apply the voltage across it, you can make a semiconductor device as actually conductor. If you turn off that, it's acting like insulator. That's why it's called the diode. You can make a 1 and 0 out of a semiconductor. So silicon is good one, and then we can use this principle as a photodetector. But what's more interesting, is okay. Let's do some calculation for the silicon photodiode detector. Same example, right? 140 kV high energy photon from technetium 9M, now interacting with the scintillator called the cesium iodide. Cesium iodide is actually a little brighter than sodium iodide. So the number of scintillation photons generated from cesium iodide from one single 140 kV is 52,000 photons per MeV. So we calculate the same way. It's about 7,000 scintillation photons. At the wavelength, about this one, it's about blue range. So energy of scintillation photons, this energy is about, do you remember this equation? So do you remember that the energy of a photon is a Planck constant, h, times the frequency? Remember this? H times nu. That's the equation I just wrote here. H times nu, but oh, not yet. Oh, not yet. Yeah. So you can just convert your frequency to be speed of light over the wavelength. Either way, if you know the frequency of the scintillation photon coming out of cesium iodide, you can just use the frequency, and then h times frequency is what we are calculating. But I just happen to know that the lambda wavelength of scintillation photon from the cesium iodide to be 540 nanometer. Yes?
Random question, is there a reason why there's cesium iodide and then parentheses?
It's the doping material to make cesium iodide to be no, it's the doping material is used for the scintillation property. Without the doping material, I think a cesium iodide is not very good scintillator. With doping, it's actually doing very good the scintillation property, as far as I remember. It's not semiconductor. Cesium iodide is a scintillator here. Yeah. Yes.
So HC over lambda is the C, like the speed of light.
Speed of light. So the equation I'm not showing here is again that do you remember that again the energy of a photon is h times nu, right? Remember that the frequency, the nu is equals to c over lambda for the light, because speed of light is frequency times wavelength. Or what you can remember is that, do you remember the simple equation about, so what is speed? When you learned in actually physics in high school, maybe middle school for some of you. So how did you learn about the speed? How do you calculate the speed? What do you have to know about the speed? If you want to calculate the speed of an object, you want to know the distance traveled over the time it takes, right? Frequency is just inverse of the time, right? So distance is one wavelength, as let's define as one wavelength of a travel of a light as a distance, divided by the time it takes. But 1 over time is frequency. That's why the speed of light is equals to wavelength times frequency. It's either wavelength time and over the time, but okay. So that's that equation. If you are in doubt, just do some derivation. This is very simple derivation. You have to be very familiar with this type of calculation. So we just want to calculate the total energy of all these scintillation photons by having known that the wavelength of the scintillation photons coming out of cesium iodide. That means that if you know the different type of scintillator, this equation will be different. You just have to know the wavelength or frequency coming out of a scintillator. So doing that, this is one single high energy 140 kV photon from technetium 99M is generating about 2.3 electron volt of energy from cesium iodide scintillator. That's what we calculated here. And then within the silicon photodiode, number of electron hole pairs we want to calculate, what kind of charges right here, scintillation light coming into the photodiode. We want to know the charge, like electron hole pair created from interaction of scintillation photon with the silicon there. That's what we want to calculate there. So number of electron hole pairs are number of scintillation photons times, this is also kind of quantum efficiency type of calculation. Photodiode conversion efficiency is the wording I used, but the same thing, What is the fraction of the scintillation photons is converted to the electron hole pairs? That's the actual signal, the charge within the silicon. For typical silicon photodiode, we are operating for radiation detector. It's about like 50–60% range of conversion efficiency. So this is actually one of the reasons that people argue very strongly that, yeah, we better use like this silicon photodiode instead of PMT, because the conversion efficiency is much bigger than photocathode conversion efficiency. The problem with of course, the silicon photodiode is that it's not amplifying. So the signal is still very weak, even if it can convert real signal to like a charge. Okay, little more calculation. So what kind of current we are talking about? As I said, that there's no amplification. So just do the calculation of the charge we calculated for this number of electrons. That's all we have to calculate. Let's say that we collect this about millisecond, not microsecond. It's not 2 microseconds is our assumption here. So let's say that we collect this, the charge over 2 microsecond. Then the current we are measuring from the silicon photodiode is now nanoampere range. This is what I was talking about. This is very low compared to PMT. So of course, this is not something that a lot of people are excited about. So what people wanted to do is that, again, when you have a weak signal, what do you want to do? You want to amplify. So you can amplify actually the signal, the charge within actually photodiode. Photodiode is actually great because it's very simple structure. Compared to PMT, it's much simple and then much it's really a lot more compact. So you can make things a lot smaller, lighter, many good properties there. So that's the reason that people argue that the silicon photodiode is better photodetector than PMT. But again, what you want to do, this is it's basically showing that how small you can make with the silicon photodiode for the radiation detector. So compared to PMT-based radiation detector like this, you can make the same thing with a very small, like a compact portable way. Like this structure cannot be like this form factor. So I was talking about there's a way to amplify the signal within the photodiode. So what we can do is that instead of applying, good enough the bias voltage across the electrodes of photodiode, we applied a lot higher voltage. You can amplify, basically you can make an avalanche effect within the photodiode. So it's really snowballing. So when you have charge, you have a very high voltage, applied across, again, very, strong electric field. Charge there, electrons could be gaining a lot of energy. It can be amplifying, cascading effect of amplification. So it's snowballing, and then that process is called avalanche. So you can make avalanche multiplication, and this device is called avalanche photodiode. The problem with this device is that it's really hard to make a large area APD. So typical APD is pretty small. Of course, you can just put a lot of APDs individually together. That's something I'm going to talk about later. But one APD cannot be really large. Of course, there are a lot of active developments about making large area APD. But even large area APD is like 1 centimeter, 2 centimeter wide. This is the area we are talking about. Again, the problem with APD, why large area is not very good, is that the amplification, like this avalanche multiplication, is not very uniform. If you apply, there is a geometry there. So if you have a large area, the amplification is not very uniform. That is not very good detector property. But again, it has very high quantum efficiency because as you remember that we are talking about quantum efficiency or conversion efficiency of a photodiode without avalanche multiplication was like a 50–60%. Now you have a lot higher voltage, and then it has avalanche multiplication there. So quantum efficiency of APD is even usually higher than 100%. So it's actually higher than original signal. That's what you can do. That's good property. But again, the large area is a problem. So what people have done after this is to make this solid state photomultiplier. This is actually, again, the combination of mini APD tiled up together, but also applying little higher voltage than usual the operating voltage of APD to make the whole, each individual cells right there. Even there, actually, there are mini cells of avalanche photodiode. There are a lot of actually small mini APDs there. But now applying the voltage to make this APD function as a Geiger-Müller mode. So what it does is that, whenever you heard about this Geiger-Müller mode of operation, that voltage is it sparks. Basically, when the signal scintillation photon hits that APD mini cell within the solid state this photomultiplier, individual pixel is actually made of many mini cells of APD. So you do not see actually small structure here. But each individual APD there is now acting as a Geiger mode operation. So individual scintillation photons comes in, it sparks. But there are many of that APD within that. So if you collect all this kind of spark signal, you can still do some energy discrimination. This is another concept after concept. Actually, Geiger mode operation, you cannot differentiate the energy of your radiation contamination. That's what we talked about. You can operate radiation detector in the Geiger mode very sensitive way, but the problem of Geiger mode operation of radiation detector is that it's insensitive to the energy of radiation. But if you put a lot of mini cells together, somehow if you actually sum all these sparks together individually and summed up for each pixel, like this small pixel there, you can have some energy information. To believe it or not, that's why we can have some energy resolution, energy information by having solid state photomultiplier. It's actually, again, Geiger mode APD. Now you understand why people say Geiger mode APD. This is a bunch of APDs there, mini cells of APDs there, operating in the Geiger mode of voltage there. But now it's photomultiplier because we are multiplying the photons by this Geiger mode in a sparking, a lot of there. Also having this pixelized fashion of rugged construction. You can also have position sensitivity because each pixel acts like each position. So we can define actually each pixel and it's connected to the different channel of readout electronics. That's how we can tell where the event happened because this is a phase to scintillator. And then we can actually tell where the scintillation light is coming from the pixel information from the scintillator. Not scintillator, this photodiode. Right? So final types of this is so the state of the current development is that for SPECT imaging using gamma camera, and I'll talk a lot more details about gamma camera after this. But for gamma camera operation, we use typically sodium iodide combined with coupled with the photomultiplier tube. That's actually usually the current. I cannot say state of the art, but the most conventional gamma cameras still commercially made of sodium iodide coupled with PMT. Newer gamma cameras actually come with the CGT detector that I'm going to talk about after this slide. Okay, that's the current state of the art for the SPECT imaging. But for PET imaging, the current state of the art is this solid state photomultiplier. A lot of older PET scanners are made of BGO or LSO, that's the name of crystal, coupled with photomultiplier. But PET scanner technology has evolved very rapidly in the recent 5 to 10 years. So in the past 5 years, now basically all the major manufacturers of the PET scanner offer SSPM-based PET scanner. It's a little more expensive than PMT-based PET scanner. Same crystal. LSO is the main. LSO, LYSO are the main crystals for the PET imaging at the moment. But same crystal, but combined with the SSPM is a current state of the art. But SPECT imaging is not actually using SSPM that much. There's little difference of even if people like myself, I don't care about PET technology, SPECT technology, but actually I do a lot more instrumentation research in SPECT technology at the moment. But again, these people kind of came from the same community and then they are talking to each other. But anyhow, the current modern technology for SPECT and PET are a little different in terms of photo detection. The last thing I want to talk about is this direct conversion solid state semiconductor detectors. This is actually, in principle, the most exciting about radiation detection, because we are not converting the high energy photon to scintillation light by scintillator. If you have a material that can detect high energy photon, but directly converting that high energy photon to charges, you don't have to have a scintillator and photodetector. You just have one detector material, and then you can just read out the charges collected in this the material directly to the readout the electronics. This is the simplest way of making radiation detector. Do you see really the connection here? So if we can have a good direct conversion capable solid state semiconductor detector, this can solve actually a lot of problems with the radiation detector, the technology for PET and SPECT. The reason this is now being adopted commercially for SPECT imaging a lot more than the PET imaging is that there are materials like this. Those materials are usually, what we are using, what we are actually developing, typically commercially used are CGT, cadmium zinc telluride. This is composite material. This is the solid state semiconductor detector, or cadmium telluride without zinc there. These materials are having, actually do have the properties I was talking about. The properties of directly converting high energy photons to the charge signal that can be read directly by the readout electronics. But this material is not really very high Z material, atomic number wise, meaning that stopping power of this material is really great for typical energy of SPECT radiopharmaceuticals, radionuclides, like a technetium-99m, like 140 keV. Iodine-123 is 159 keV photons. This material can stop very well without having a lot of thickness. 5 millimeter CGT material can stop like 80% of 140 keV. Don't quote me, I don't remember exact number, but it can stop very good fraction of 140 keV having just 5 millimeter CGT material. But the problem, again, is that it cannot stop very well for like 511 keV photons for PET imaging, right? For PET imaging with this type of material, you probably want to have like a 2 centimeter, 3 centimeter type of thickness. For scintillator, that is okay. But this kind of direct conversion, because the charges are generated internally there, and then you have to drift this charge and then collect that charge, the thickness really matters. You cannot really have a very thick, the detector like this. So that's one of the reasons. Of course, and people try to use this type of material for PET imaging. So direct conversion is just like this simple diagram. It's just this, the operating principle for direct conversion solid state detectors. Okay. This is our CGT material or cadmium telluride material. There, high energy photon. This is not scintillation photon, high energy photon interacting directly within the semiconductor material like a CGT, and it produces a electron hole pair directly. And if you apply high voltage across it, again the same principle, you can drift electron hole pair. You can collect the those charges by the electrodes. You can just read without electronics, right? The simplest operation of radiation detector. Of course, people have made again that commercially, this is now being offered. This is not major. Unlike PET imaging technology, again, the direct conversion like a CGT-based SPECT technology is part of the portfolio of SPECT scanners, but not like 90%, not like 70%. Maybe 10% of commercial SPECT scanners are based on CGT, direct conversion semiconductor detectors. Unlike now probably 50% or more of PET technology is based on solid-state photomultiplier as a photodetector. So this is kind of the chart showing, the table showing kind of a gross view, like a overall view of the differences between gas field scintillation-based radiation detector or direct conversion solid-state detectors. Spatial resolution is questionable. You can actually make even scintillation to be very good spatial resolution, but this is kind of typical number we are talking about. You don't really have to care too much about gas field detectors because we are not using it for the imaging. We are using a lot of gas detectors for like safety purpose. Scintillation-based one, 4 millimeter versus like a 200 micron. Of course, you can make actually scintillation-based one to be even some 100 micron range. But most important thing about this comparison chart is energy resolution. The second property there. Scintillation material, even for sodium iodide, we are talking about 8% of energy resolution. 8% percent. I'll give you some more definition about the energy resolution later. But the smaller number for energy resolution is really better energy resolution. How well we can define the energy is what we are talking about energy resolution. The smaller the better, of course. That's how you can distinguish different signals. But direct conversion solid-state devices like a CGT or cadmium telluride, you can have 1%, 2% energy resolution very easily. You can go even down below 1% energy resolution. You can make an energy spectrum really sharp. That's the biggest advantage of a direct conversion solid-state device. If you need that high of energy resolution, or if you know how to use very good energy resolution to your own advantage of making better images out of your imaging device. The problem of a solid-state device like direct conversion is that, of course, the stopping power for PET imaging is questionable for the good operating the characteristics. But another problem so far is that the cost is still pretty relatively high. So that's actually one of the reasons that even if for SPECT technology, people love about like a CGT-based SPECT, but the commercial companies do not offer like 100% of their scanners made with the CGT, is that cost issue. If you if you have product, but this product compared to conventional technology is like twice more expensive. So that's why they are making still large number of gamma camera SPECT devices with the conventional sodium iodide with the photomultipliers. For PET imaging, of course, SSPM based one is a little more expensive still, but somehow commoditization is really happening, and then I think price of SSPM is going lower and lower. They are offering little higher price for using modern technology, but still, what can I say? Still a little more expensive, but very comparable to conventional like older technology. That's kind of the current state of the art, which means that next year this story could change. So any questions so far? So I have some recommended reading. If you want to learn about the current state of the art knowledge for physics of interaction of particles with matter, the best material is going to PDG, Particle Data Group, based at Berkeley. But it's not like a Berkeley people. This is a group of international physicists compiling the current standard knowledge for the physics. So they have actually big book of each chapter describing all these different physics, and they always want to have up-to-date information. So if you go to pdg.org, you can actually even download the entire particle data group's publication about current physics. One of the chapters is about passage of particles through matter. This is exactly the physics that we talked about, interaction of charged particles, interaction of radiation with matter. Okay, this is really the best material you can find. Of course, if you're really interested in learning about the radiation detection principles in general, this is the textbook that you certainly have to consider buying. Glenn Noah was actually giving some small lectures about radiation detection, coming out of his textbook at the one conference he attended, regularly. But one thing I heard about him was that because he's teaching from his textbook, he also wanted to sell his textbook. I mean, not bad, it's really very fair price. It's a discounted price. But that is not available anymore because he passed away a few years ago. Any questions? So why don't we take a 10-minute break, and we can resume to the fourth part of my lecture. So any for the location of the class, I think except myself, I think everyone else is still sticking to the classroom. Projector or not projector really doesn't matter. Somehow, I think it's more about the personal preference. I wanted to have this room from even the beginning, but I think a lot more people prefer that room. I think one of the reasons is also people tend to use whiteboard, as you could see. I tend to use not to do anything, I don't know. I just do not know. I mean, I loved the writing on the board before, but these days, no. And then I really want to have a closer proximity, and I actually want to sit, and I have some standing issue. So unless I email you before the class, we are going to meet here because there are still like a few days that the room, this room is not available for this time frame, also even 209 of my part. So I'll let you know. And also, as I mentioned before, the calendar does have a correct information about location. I made sure that timing and then location-wise, I updated all the information very carefully. So now we are getting into the measurements and the radiation dose discussion. So this is actually one before we will be talking about the actual imaging of our interest, those high energy gamma ray and then X-ray photons. So we learned about radiation detectors. So let's go over this one more time. So we have some radionuclide or radiopharmaceutical most of the time. So radionuclide as in the form of pharmaceutical. Now it's a radiopharmaceutical. So there's that radiopharmaceutical, distributed in human body or animal body or some object is emitting some, emission, like gamma emission, or this could be actually X-ray like transmission from X-ray tube. But that X-ray or gamma ray is hitting radiation detector. And from radiation detector, remember that the final signal out of radiation detector is the voltage we are measuring. So by applying the high voltage through the detector, the signal coming out of here, right there, by without electronics, is the voltage. So without electronics also could be combined with the amplifier again. So even after amplification, by PMT or silicon photon multiplier, avalanche photodiode whatsoever, that signal is still weak. You want to amplify really further to do any kind of hardware level image processing. This is not actually image processing, signal processing. So for the signal processing of the signal coming out of the radiation detector, you want to do amplification of that signal, voltage signal, by putting preamplifier first and then amplifier. This is a very common way of amplifying the signal. You're not actually just putting one amplifier. You want to shape and refine your shape of voltage signal, then you amplify. So that's why you put preamplifier first and then amplifier, right? Remember this one, preamp, amp. Have you done any analog audio manufacturing? Vacuum tube based audio, whatever. This is very good. Anyhow. Then you'll learn about what I'm talking about very easily by just really hands-on experience. Or even not building, but have you ever considered investing in really some high-end audio equipment? Then you also learn about you should have a separate amplifier that is also connecting to different devices, right? Remember that? Yeah. Amp is always a separate device. So when you have your voltage signal amplified enough, then you want to do some analysis. This is a type of the signal processing for our imaging devices. The pulse size analyzer is one mechanism there, and then we do some scalar timer. We got to know actually time it, and then some scale magnitude of our signal, and then we have to know also how to analyze the height and then shape of our voltage signal. That's what it is. So photon counting or pulse counting detector system, usually made of all these components we just described, the high voltage supply, for actually making radiation detector work. And you need to have, really a preamplifier, amplifier, whatever amplifier, combination, whatever that you condition and actually increase the size of the voltage signal. And the pulse site analyzer, this is very important to collect the data that we want. We want to actually reject the data that we do not want. So you need to have some mechanism to do that. That's what we are using this kind of signal processing called the pulse height analyzer. Scalar and timer are very important when we are counting something. So this is how kind of pulse height analyzer works when we have only one single channel. Single channel meaning that we are reading just one channel of information. Okay, I'll talk about multi-channel analyzer after that. So we want to talk about single channel analyzer first. So as I mentioned, that single channel analyzer is that depending on the pulse height. So that's why it's a pulse height analyzer. With the single channel, we just say single channel pulse height analyzer. So what we want to collect is, within a range of, pulse height, we want to collect the data as like a 1 or 0. We want to collect or not collect based on the pulse height. So in this single channel analyzer, in this diagram, we are only collecting the pulses with the magnitude within the window of this channel. So if pulse height is between this upper energy window and lower energy window, like this signal, this pulse, for that pulse, it will be accepted as signal. But if it's higher than that, the window, or the lower than the lower energy window and level, then it will be rejected. So we are counting the pulses. Again, we are not really, getting all these analog type of pulses. We are actually counting pulses. This is one pulse, the other pulse, right? But we only count the pulses within a certain range. The magnitude of a voltage signal from our radiation detector is related to the energy of an incident photon. Right? Remember we talked about how much of energy is generated from that interaction by calculating how many like a scintillation photons are really generated from scintillation process. We calculate all this just to know that incident photon energy is related to the final voltage signal, and the height of the voltage signal is directly corresponding to the energy of incident photon to the scintillator or direct conversion detector. So in this, what we are doing is that we want to discriminate in a certain energy of the signal event. The events could be actually lower energy or high energy depending on actually processes happening. There are a lot of interactions, a lot of process happening from the single photon interaction with the detector material. Right? So this is basically energy filtering. We are counting the pulses, the photons with a certain energy. That's what we are doing. Not really the delta function of energy. We should have some range because energy, resolution is not infinitesimal. Yes.
How do you decide which pulse height window you want?
Oh, for that you actually do some of this multi-channel analyzer first to do that. If you know how to do it, you can go back to single channel analyzer. But most of the time, what we do is, what people do is that it's a multi-channel pulse height analyzer. This is actually a way to generate energy spectrum. You gotta know energy spectrum. The energy spectrum is basically shape of photon counting. Frequency of photons and different channels is energy spectrum. Still, it's can I say? I'll take some time to explain this one. This is probably not so straightforward concept. From multi-channel analyzer, so this diagram shows how a multi-channel analyzer works. We have multiple channels. So instead of having single channel, so collecting really all the pulses within this channel, what we are doing with the multi-channel analyzer is basically we have multiple channels. Usually it's a continuum of channels like this. So pulse height is corresponding to the energy of incident photon. Remember that? So these channels, let's say channel 1, 2, 3, 4, 5, 6, okay? This lower number channel number, so the counted pulses in the channel number 1 is corresponding to lower energy signal. You see that? And then channel number 2 is corresponding to higher than channel number 1. 3 is higher than channel number 2. Okay. Now think about this way. We are making histogram. Frequency is very important. How many pulses in channel 1? How many pulses in channel 2? How many pulses in channel 3, 4, 5? If you have a lot of channels, you can actually convert this type of analyzer to energy spectrum. So use this multi-channel analyzer to collect the data, and then when you collect the data, you can histogram how many pulses within each channel. Each channel could be plotted on x-axis from lower energy to lower channel to higher channel. But lower channel is lower energy, higher channel is higher energy. So your x-axis on the right figure, it's basically histogram from collecting the your signal by multi-channel analyzer. But frequency of each channel is a number of counts, right? This is a basic histogram. That histogram from multi-channel analyzer is exactly what we call energy spectrum. Do you see the connection there? So when you have an energy spectrum, your x-axis is just channel number, or you just know that the channel number is proportional to energy of incident photon, but you do not have an absolute scale. Now you also have to know how to make that as absolute scale. How would you do that? This is what people do, really. I'm not kidding. This is exactly what is happening when you are doing some hardware, work in this area. So when you have your detector made up fresh new, and then you did this multi-channel analyzer, and then you actually make some energy spectrum. Now you want to actually have this energy spectrum to have absolute physical scale, the real true physical scale on the x-axis. You want to know actually channel numbers are corresponding to what energy. How would you do that? Again, we are going back to the standard. If you have a standard, if you have a radioactive source usually, because radioactive sources emit gamma rays, depending on whatever radioactive source you have to choose, that you know that there's only single energy level emission. That's your standard. If you have some, let's say, cobalt 57 as your standard. Cobalt 57 is radionuclide that emits, what is it, 120 something? I don't remember exactly, but it's very close to 140 kV, but single energy level gamma ray emission. So if you use cobalt 57, if you get that energy spectrum of cobalt 57 using this type of multi-channel analyzer, produce energy spectrum, you can see the peak of that single energy. So you can define that peak as your channel number corresponding to that energy. You can make a scale. You can make actually this conversion from the channel number to the energy level by having multiple of these measurements. So you just have to have some low energy emitting radionuclide, some high energy emitting radionuclide, some intermediate energy emitting radionuclide, do the measurements, find the peaks, and then you can derive the conversion equation between channel number to the energy level. Then you can make actually real energy spectrum, and your x-axis could be labeled as a keV or MeV, whatever. So once you know that, then you know exactly which peak you have to collect. Then you can actually do single channel analyzer type of collection if you do not care about collecting multiple energy windows. If you want to just collect one type of signal coming from just one type of radionuclide, you can do single channel analyzer to just count of the photons. Of course, this can be done, but with a multi-channel analyzer most of the time, because sometimes showing and then looking at the energy spectrum itself is very important as well. And then many times we want to collect multiple energy windows, multiple actually channels. Instead of just collecting one single channel of a data collection, we want to collect maybe channel number 4, channel number 6, channel number 2 at the same time. I'll describe why we want to do that in the later slides a little bit. Are you okay with this multi-channel analyzer energy spectrum? Okay, now energy, the detection, the radiation detection. This is what's happening. Again and again, we have the same kind of diagram. Let's look at the same thing over and over, but little different perspectives. So now our high energy gamma ray or X-ray, the incident photon, is hitting the detector material. It could be scintillator, it could be direct conversion solid state detector. Okay. Let's say this is scintillator. Coming in, making interaction. Detector should have, the scintillator should have enough stopping power so not to lose this incident photon. So somewhere in the detector, it makes interaction. When it's interacting in ionization process, some photoelectric effect, Compton scattering, that's what we talked about, right? Those two are the dominant interactions for our energy of interest, basically. So during that kind of processes, some ionization, like electrons could be coming out, and some of the other things are coming out. Usually, those electrons are stripped. That's ionization process. But assuming that those electrons are all still absorbed within the detector, then the signal we can collect from detector is basically corresponding to the entire energy of this incident photon. Okay, but that's not really what's happening every time. There are some other components of the things that could happen. So that's what we are going to talk about. So if we could observe everything energy related by energy conservation rule, if we actually collect everything, even any process, whatever, or whatever energy containing thing is observed within the detector, and then if we collect the charge very precisely by our radiation detector, and let's say that our radiation detector has a energy resolution, meaning that how precise we can measure energy is basically infinitesimal level, delta function level. Then this is energy spectrum you'd expect, right? If it's coming from single energy gamma ray, right? Just one line is what your energy spectrum should look like. But again, that's not the case because there are many other factors. First factor is that our radiation detector is not perfect in terms of energy resolution. There's some blurring happening about the precise measurement of the energy level. And also, this interaction is not always like 100% observed like this way. Let's look at the more practical energy spectrum. This is a very practical and then very popular energy spectrum people are showing. This is energy spectrum of cesium-137, measured by sodium iodide with the thallium doped type of radiation detector. Cesium-137 emits gamma ray at the single energy level, which is at the 662 keV range. It's really high energy, but again, this is very good example of showing what could be really realistic energy spectrum looks like. So energy spectrum of this cesium-137 apparently, obviously emitting gamma rays at single energy level, 662 keV. But you see it's very blurry curve here. It's not clean, single line curve like this. What's happening here? We want to know what's happening here, everything. We talked about photoelectric effect and Compton scattering. Okay, so if the photon is completely absorbed through the interaction with this electron in the electron cloud, then the high energy energy is actually really high enough that it ejects some photoelectron. This is photoelectric effect. So actually here again, what we know is that all we care is that actually incident photon lost all the energy through this one. So something we could miss is this ejected photoelectron. But electron is not traveling that far. Usually, whenever photoelectric effect is happening, basically all the energy is deposited somewhere in the radiation detector, except you lose some part of ejected photoelectron. But unlike a photoelectric effect, when Compton scatter happens, what is Compton scatter? You remember that the incident photon is still surviving. It could lose some energy by scattering. It's transferring energy by the scattering process to the electron in the electron cloud, but it's still surviving, having, like a scatter photon still, traveling within the detector material. So to be completely absorbed, this scatter photon should be also going through either photoelectric effect or Compton scatter, and then everything should be buried in the detector to have a pretty clean signal. But that's not what's happening usually. That's why there's some Compton-related spectral components. So we'll talk about it one by one. So scatter is the common culprit about having lost some energy and then some kind of dirty part, the component of energy spectrum, because of scattered photon like this could be even escaping completely out of the detector system. Also, if a scattered photon is detected, it's another photon is recorded by the radiation detector. But scattered photon is not the same energy as the incident photon, meaning that energy of the scattered photon measured, detected by radiation detector will be lower than the peak energy of the incident photon. So I really urge you that you really got to remember how to, really calculate whatever related to Compton scatter very carefully. Photoelectric effect is, of course, very important. It's a lot easier to calculate whatever properties we're talking about. But Compton scatter is a little more complicated because of there are, multiple components of, the before and after interaction. Do you want me to go over this equation? This is, okay, here, okay. So here we know the energy of an incident photon to be Planck constant times the frequency. As I explained before, the frequency could be just written as the speed of light over the wavelength of the light. Now, as I said that the scattered photon from this elastic collision is a lower energy, but the lower energy still has a frequency and the wavelength. We just put prime because this prime indicates that this is from scattered photon. So this frequency should be smaller than the original frequency. This should be larger than the original wavelength. And then the energy of a scattered photon is like defined this way. You can derive this one. Again, I do not want to derive this one just on the board, but you can find this equation. This is really how you can see that. You can see, you know, whenever you see any equation, the first thing you want to make sure is that this doesn't make sense. Does it make sense? Let's say that if a cosine theta, this is a scattered angle, is 0, meaning that incident photon scattering, but scattering is basically it didn't happen. You didn't lose any energy, right? So that's why if theta equals to 0, your scattered photon energy should be exactly the same as incident photon's energy. Does it make sense? If your cosine theta, theta to be 0, meaning what? Cosine theta is 1. So this is 1, right? And then this entire thing is 0. So this is exactly h nu, the same as the original energy of incident photon. Extreme cases, how the scattered photon could be, so how incident photon could lose the maximum amount of energy. What kind of scattering should happen to lose the maximum amount of energy? When incident photon makes a scatter angle to be 180 degrees, when it's a head-to-head collision, and then scattering is happening just back like this way. That's the time that it loses the maximum amount of energy from Compton scattering. How can you make this equation to be the maximum value? When you can make your denominator to be the smallest out of this equation. When is the condition? What is the condition to make your denominator here to be the smallest? When you can make cosine theta to be 0. That's exactly 180 degrees, right? Do you see that? All other components are, you know, all constant. We already know all the values. H is Planck constant. Mu is already known value. This is frequency of incident photon. M naught is, yes, this rest mass of electron. G squared, speed of light, everything is constant or known value. The only variable here is a theta here. So the conditions really do make sense, right? So either you want to drive this one, I'm fine, but you know, again. So from, you know, another derivation, you can derive the difference between the wavelength of, so it's lambda prime minus lambda is what we are showing here, is in this property. You can actually really derive from these equations. This is pretty easy math you can do. Some of this is not something you want to remember. This is something you want to probably remember. This is the most important equation. Again, this is also a simpler way of calculating quickly about some of the properties. Energy is like this way, and you can convert all the energy unit to be kV and actually per angstrom. Angstrom is also not very popular unit these days because people tend to use nanometer, I think, a lot more these days. But angstrom is 1 to the, 10 to the minus 10. So, you know, this is just easy way to convert anything with this kind of unit. So if you follow this unit, delta lambda, the change of wavelength could be also written this way in angstrom. But again, this is just kind of shortcut equation. This is not fundamental equation we derive. The only thing that you can remember, you know, you have to remember is this equation, and you can derive everything. If you are not very sure to derive everything, then you want to remember some of other equations. Of course, I'm not asking you to remember, you know, the value of a Planck constant or the speed of light. You know, of course, I do remember some, you know, values, you know, for some of constants, like speed of light is something I remember. But Planck constant is something I don't remember. This is very, what can I say, complex number. What is it? It's very big number. It's like alarm frequency and other things you have to remember. But all those constants will be given if I give you any, the exam question. Another good trick to remember the constants is that I actually saw the like a mug cup with a lot of constants actually written there. That's something you can get. Anyhow, anything like that is just too redundant. You don't really you're not expected to memorize all those values. But some of again the equations like this type of equation, unless you do not know how to derive this one, except for the final exam, you can basically bring your formula sheet. I really expect you to remember at least one equation like this. Okay. Now we are going back to the spectral components. Why we explained this photoelectric effect and then Compton scattering again, because to explain what's happening in the spectral components, we need to have that concept again refreshed. So there is a photo peak, Compton valleys, Compton edge, Compton plateau, and X-ray escape peak, backscatter peak, characteristic X-ray, and some peaks. These are the spectral components. Let's explain these things one by one. Again, the purpose of understanding energy spectrum is that we want to know which part of a spectrum is the signal we want to collect, we want to count. Okay. Compton scattering happens a lot of times. It's very common the event happening in the radiation detector. So what if incident photon coming into radiation detector, scintillation material, Compton scatter happens, some electron, like RICO electron, is still there, but the electron is usually observed. But what if even lower energy photon escapes from the detector, meaning that this amount of energy is not recorded by the detector, right? Not recorded. So there is still signal, but the signal should be measuring lower amount of energy because of there's some loss of scattered photon. Another thing you have to remember here is that this scattered photon's energy is not fixed. It could be anything within the Compton scatter equation, right? This is what we are showing. This is anything. Energy loss is anything. This is what I told you when we have a 0 versus 180 degree. This is the energy we are talking about. So because of that, we have this kind of Compton scattering related spectral component in the energy spectrum, because the detector is measuring the energy, right, of incident photon, but that energy is not sufficient because it lost some Compton scatter photon escaped from the detector. But that's kind of continuous. The maximum of that Compton component of energy spectrum is defined when we have delta to be 180 degree or pi. You know how to calculate between 0, pi, all these things, right? Do you? 180 degrees pi, 2 pi is 360 degree. And when you do use radian as your unit, you want to use pi, 2 pi, those are real numbers. This is real number in radians. It's corresponding to actual the angular degrees. So this is Compton component of energy spectrum. And there's Compton edge for the maximum energy of loss. And then there's a minimum energy loss, whatever. And then this is continuum of the kind of recording because of the loss of energy by the loss of a Compton scatter photon is continuous, right? That's a Compton, the part of it. Now, I want to talk about what is the X-ray escape peak. Another thing that's happening is that when photoelectric effect is happening within detector with certain material, let's say this material is containing, this scintillator is containing iodine. Sodium iodide or cesium iodide does contain iodine. Iodine is actually a lot bigger, the atom, than the sodium or cesium. Okay? When the incident photon interact primarily with the iodine, like atom of your scintillator, ionization electron happening, right? But again, when you strip the electron, K-shell electron of iodide by incident photon. And then that electron is now stripped, still recorded, but when K-shell electron transitioning to K-shell and there is a X-ray coming out from that process, right? That X-ray photon right there could be still absorbed by detector. What if that X-ray from iodide is escaping from the detector? That happens as well. It's not 100%. This X-ray, characteristic X-ray of iodine, which is exactly 28 keV. 28 keV is the difference between K-shell and L-shell energies. Right? If this 28 keV is escaping the scintillator, then you are losing that much of energy. So whatever signal from this process measured by detector is losing that much. So there should be some measurement around that energy, not actually photo peak energy. Photo peak energy is really single, the original energy from the gamma ray. But now we have another peak, but with the very distinct separation from photo peak. That's actually X-ray escape peaks. I'll show you the energy spectrum later about. Some peak is a lot easier to understand. When we have an incident photon, but that photon could be actually, we are not talking about one, we talk about one at a time. But what if two incident photons traveling, it's not, it doesn't have to be like this way, but two photons interacting with the detector, whatever direction is fine. But what if those two interactions from the two incident photons are happening about the same time? About the same time meaning that your readout electrons cannot distinguish time-wise those two interactions. If they are measured about at the same time, that cannot be distinguished by your readout electronics, right? Those two interactions are just recorded as a single event. But the energy level from the single event coming out of two interactions is exactly twice of the energy of incident photon. But what I'm saying about some peak is sum of 2 or 3 or 4 or 5, whatever multiples. So if 3 photons happening at the same time and measured at the same time, the sum peak of 3 photons could be 3 times of the photo peak of a single photon. Of course, the likelihood of having 2 peaks, together, some peak is much more common than like 3 photons summed or photon sum. So some peak is very obvious actually from energy spectrum. You can see it actually if you measure anything like that. You see the some peaks very, very clearly. Now there's one more that I want to talk about before going back to the energy spectrum again. So backscatter is happening when the source, a radioactive source, is emitting some gamma ray. Of course, we want to detect radiation from the source by the detector. But you cannot actually have everything just the vacuum versus source and detector. There should be some material around it. Source is usually contained. Also, detector is usually contained by some other material. So what if the radiation, like gamma ray, is interacting with some surrounding material? And then what if the scatter within that material and the scatter photon escape that material, but if the scatter photon is going back to the radiation detector? That's why it's saying that the backscatter photon from the surrounding material. And those backscatter photons could be recorded by radiation detector. This is unwanted, it's unintended, but this happens. So this is what's happening about backscatter. If we just take one example, what if we have a hypothetical photon, it's radiation gamma ray. This carries about 500, no, not about, exactly 500 keV energy. It's constant scattered by angle of delta, the angle to be 180 degrees. The wavelength and the energy of this scattered photon. You can do this calculation. We actually talked about this one. This is not particularly about backscatter, it's about Compton scatter. So I think I have to drop that slide. I don't like that slide. No. So anyhow, so I just realized. So 187, cesium 137, the NS spectrum measured by sodium iodide. I showed this picture again, right, before, but showing this as NS spectrum again. Now we can understand what this NS spectrum is really telling. Of course, the photo peak is actually coming from the, really the incident, the energy, the photon energy, which is 660 keV or 2 keV. There should be some peak about that. But there's this iodine escape peak, which is separated by 28 keV, because this is a characteristic X-ray of iodine. So all the energy is recorded, but we lost exactly 28 keV because of some of this X-ray from iodine atom, that is lost. Then we have this peak at the, 662 subtracted by 28 keV. Compton, right, edge, and continuum. And there's some backscatter Compton from the surrounding material. And there's a characteristic X-rays detected. This characteristic X-ray could be coming from, again, what if those 28 keV is actually recorded again as a separate event? You can measure some 28 keV peaks there. And then there are other materials around the detectors. Not only backscatter, okay, it could have also X-ray emission out of this material. Why X-ray emission? The same thing. Photons interacting, photoelectric effect, and then there could be some X-ray by transitioning from K shell to A shell and L shell to K shell. And this X-rays coming from all these different materials around it, including the detector material. There are some portion of X-rays coming out because of all these issues. So there are multiple characteristic X-ray peaks depending on what X-ray, material was, really the source for this characteristic X-ray. You can actually see the different materials by looking at characteristic X-rays measured by energy spectrum. Right? And then, of course, you can see some sum peaks for the cesium-137. The sum peak should be 1,324 keV when two interactions are summed together. If 3 and there's something like some peak around here, there. Any questions about that? So we do understand now what kind of energy spectrum we expect from the combination of everything we put together. Yes?
Can you describe real quick, like exactly why the Compton effect has like the plateau, the edge, and the valley?
Plateau is that this continuum of energy. So we can go back to which one is better? Let me see. This one. So the measured energy is a part of energy spectrum, right? But that measured energy, when the Compton scatter photon is not recorded, the measured energy is still continuous because of the scatter photon energy is also continuous, right? This could be not just degree. For making this exact angle, this is fixed number, but escaped scatter photon could be making this angle, that angle, that angle, whatever angle. So whatever angle, 0 to 180 degree, depending on the angle, your energy, the energy of scatter photon is different, but it's also continuous. That's why you see the continuum of this Compton related, spectral component. And it has edge, and then, because of there's some maximum, minimum-ish there. All right. Any other questions? Yes?
The Compton interactions only happen with artificial electrons or
No, it happens actually mostly, with inner shell.
So can you get X-ray emissions as well?
Yeah, of course. X-ray emission happens quite a lot whenever there's ionization process, yes. Any questions?
Yeah, even if it interacts with the in L shell, there is also the higher energy state, electrons there. Whenever there's ionization process, there should be some, the transition of electrons. But when you have this L shell and higher shell, the difference of those are, I think, smaller. Is it smaller? Anyhow, those pretty low energy. It's not usually seen on the energy spectrum. So the reason also we talked the really iodine escape peak is that this separation is pretty large. K shell, L shell difference. This large 20 keV is, because iodine is a higher atomic number, the atom. If it's a lower atomic number, that difference between K shell and L shell energy is very small as well. It's not this distinct. So if we are talking about escape peak for like a sodium or cesium, part of sodium iodide, scintillator or cesium iodide detector, I don't remember exact number, but it's very small. It's not actually seen distinctly like this. It's kind of buried because of this limited energy resolution. Any questions? Because yeah, I'd like to end today's lecture now, so we can continue on Tuesday next week.